Welcome to Web Application Firewalls, analysis and detection of detection logic with Vladimir Ivanov. Before we begin, a few brief notes. Stop by the business hall located at Bayside, AB. Black Hat Arsenal is in the Palm Foyer, level 3, and the Arsenal reception is going to be at 5 p.m. today. If you have not picked any merchandise or t-shirts or books, today is the last day. You can stop by the Black Hat bookstore. And you can visit the Kali Linux lab in Mandalay Bay A. Thank you for putting your phone in silence mode. We appreciate that. And please give a warm welcome to Vladimir Ivanov. Thank you.
Check, check. Hello, everyone. Thank you for joining the session. Right. My name is Vladimir Ivanov, and in my presentation, I will be talking about new old methods which help me to attack replication firewalls. I will be discussing new ways to implement own security approaches in finding security vulnerabilities. I will be also releasing some tools, cheat sheets, and recommendations. But before we get started, a little disclaimer. Most of the attacks and breaches I will be discussing are 0 days. So due to the nature of the bypasses and due to the amount of affected rules, they cannot be fixed in a shorter time. Hence, as far as I know, some security teams have already patched their issues. Some of them are working on a fix, but some flaws will not be fixed forever. So this presentation is aimed to bring attention to the design of detection logic of web application firewalls. So the schedule for 45 minutes is as follows. We'll be first discussing motivation and aims for detection logic researchers from a higher perspective. And we'll go pretty fast through the history of WAFs and understanding how web application firewalls work. After that, I will be describing 3 ways to attack web application firewalls, as you can see on the slide. But one is something I call method of finding syntax-based bypasses, in which I'm going to present a tool which can assist with finding flaws in regular expression detection logic. Moving forward, I will highlight the method of finding logical bypasses. And finally, we'll go through the method of finding unexpected by primary logic bypasses. You'll get the idea what's that in my session. So let's get started by inspecting the standoff between the attackers and defenders. When the typical attacker faces the web application, which is protected by the web application firewall, he's doomed to try all possible evasion methods that he knows he has ever read in blog posts or ever watched on YouTube to evade the filter that said encoding payload, uppercasing, lowercasing strings, inputting characters in a various type of payloads, etc. So in a likely case, if a bypass is found, he doesn't face the need to dig to the root cause of the problem and to report it to the vendor. Well, on the other side, defenders very rarely analyze the logs of the web application or web application firewall, and hence they're helping attackers to achieve the goal, and so the attack will go undetected. The irony behind this global standoff is that usually there is a single person or a likely group of security engineers who maintain those rules both sides rely on. So at the fact that it is very hard to maintain the rule set which another person has created because they are maintained for years, and you can not always correctly identify the intent of the first person who's written the first rule before you. All right, so let's take a look at the typical HTTP workflow example when the web application firewall is passed between the web application and the real world. You can see 5 stages here, and from the security perspective, 4 of the stages are very well researched, and they are common between various implementations of web application firewall. But the only stage that differs is stage number 4, application of detection logic here. So we're going to analyze that. You can see some blue bubbles here. These are types of detection logic currently implemented in latest open source web application firewalls. So there are 5 types over there, and also the names of the web application firewalls which are using that. You can see that the regular expression-based detection logic is the most popular implemented type. And I can find 2 reasons behind that. The first one is that it's historical. I mean, the very first web application firewall was based on regular expressions. It was back in 1997, I think. Another reason is that regular expression are simply to understand, so the mental simplicity. Human beings like understand this syntax. All right, so since the overwhelming majority of application firewalls use the regular expression detection logic, I'm going to analyze that in first 2 parts of my talk. So anyone of you has ever written at least, say, 10 regular expressions in their life? Anyone? All right. Someone. So I would just be skipping this slide quite fast. Well, regular expression is a sequence of characters that define a search pattern. This is a quote from Wikipedia. And it simply means that there is a string defined of different wildcards and syntax, which attempts to find the substring in the source text. This is the very simple example from one of OWASP core rule sets rules, which attempts to search for HTML injections. You can try to divide this whole regular expression into 3 small blocks. First one makes all of the rest of the regular expression case insensitive. Second one searches for the open bracket script. And the one is anything after that. All right. So 6 open source web application firewalls of my personal top were chosen as the main source of the research. So I have just simply collected all of those rules from all of those web application firewalls, downloaded that on my laptop, and here we have more than 500 regular expressions. As you can simply see, there are almost 85% of regular expressions which protect the user and the server from SQL and cross-site scripting attacks. Just to give you an idea about the research, the results are as follows. I have, using all the tools I'll be releasing, I found much more than 300 potential bypasses. By potential here, I mean that it is computationally hard to generate and to verify the bypass for each rule. So you can sometimes have to verify the bypass manually. All right, so due to my personal practice, I believe that some of the inspected rules may have security flaws which were caused by the syntax, by the covert syntax of regular expressions, and their inaccurate and insecure use. So the main challenge about finding flaws in regular expressions here was the fact that widely studied by security community of application firewalls, which I mentioned at the previous slide, with high security standards, I believe that they don't have any flaws because they're open source on GitHub more than 10 years. And so in order to find all possible and impossible mistakes that probably were in this rule set, I had to find all the typical problems that regular expression have and invent all the problems that I cannot face, but I think they are there. All right, can I ask you, dear audience, to play the fast game, which is called What's Wrong with Regular Expression? Well, actually, there is a regular expression which attempts to find attack payload in the get parameter A, and if in case there is no attack payload found, it executes some very important function. So can I ask you to find 3 ways to bypass this regular expression and execute attack payload in the function? Can you name 3 of them? Sorry? Yes, right. So one of these wrongs with the regular expression is that there is a quantifier 1 to 3. The number of repetitions is 1 to 3. So you can supply 4, the string consisting of 4 attack payload, attack payload, attack payload, attack payload things. So yeah, do you know another one? Sorry? Oh yeah, right. So yeah, another one is, I think I have it here. Oh, all right, there was a hint. Right, the first one is that regular expression doesn't use the case modifier I, and you can bypass the string by lowercase and uppercasing some of the characters. And the obvious one here is to use the modifier I. Another one is, someone told that, is to use white spaces before and after the regular expression. In most syntaxes like HTML or SQL, the white spaces don't break the syntax, so you can bypass the regular expression and still execute the malicious attack payload. So the wrong here is not to use the symbol of the start and the end of the string. It's pretty obvious. And yeah, and the one which was already said is that the use of repetitions is not very good. You have to verify manually whether that is better or not. Another example here was found during my during observation of OWASP text and during my personal experience while reading the code. So this first issue here is vulnerable to attack called REDOS, or regular expression denial of service. The bad thing here is that attacker can construct the string consisting of, say, 10 or 20 or more A's, and I mean the letter A, and making the parser of regular expression to calculate, to apply this string to the regular expression a lot of times. I mean, 2 power n. So if you supply the string of 10 A's, that's 2 power 10. That can sometimes make the parts of the regular expression to fail or to execute for a lot of time. Another flaw or particular wrong here is the use of wildcard S, which is the white space and all of the new line symbols, is the use of the modifier plus. So that basically means that you can bypass the regular expression by supplying 0 spaces. I mean, A quote B would bypass that. So you should watch for repetition symbols. Another key thing here is blacklisting wildcards in a set is not also a nice thing. Is you can bypass the blacklist by using alternative symbols. So the new line character \n has an alternative of \r, and this can bypass the blacklist. Right, moving forward, while reading the documentations, I thought that people can make typos. For example, while specifying the diapason A to Z, you can basically occasionally uppercase the letter A, making this diapason not only from A to Z lowercase, A to Z uppercase, but this diapason also includes 6 additional symbols, such as opening bracket, closing bracket, backtick, backslash, I think, another one. So this is not something the developer may want to allow in user input, right? Another example, another issue here is the wrong usage of POSIX character classes. In this example, the character class was not followed and has not the starting colon here. And this is not the POSIX character class right now, but it is simply a set of 4 characters, D-I-G-T. Next wrong, which could be potentially faced while developing regular expression, is the wrong usage of operators. Developer can occasionally put a white space before or after the logical or he can supply doubling operator, which can change the logic of regular expression. And the last issue, which I'm going to describe, is the usage of backslash with the character after that. For example, \11 here, depending on the context of the regular expression, depending on the parser, can be parsed in several ways. I mean, that could be 11th backlink /11, or that could be the tabulation symbol. I think that is octal 0x9. /E is a rarely used wildcard, which is not actually documented in very places. And /Q is simply a symbol Q with a backslash. It's just simply escaping the symbol. So you can not, while watching the regular expression, you cannot say 100% what is that. So you should overwatch all these issues manually. All right, so when I was collecting all these potential bypasses, and when the number of these wrongs overgrow, I think 20 or 25, I decided to collect them into the table with detailed description, examples, and examples of bypasses. And that actually resulted in a table which is open source on GitHub. I will show you the link after this slide. And since I wanted to hack all the regular expressions I had on my laptop, remember the web application firewalls, 500 regular expressions, I coded a tool which can assist with static analysis of the code with as low positives as it could be. So here it is. Here's the link to the GitHub, regular expression security cheat sheet. This is the table. If someone of you who doesn't see all those small letters, I think you can just visit the link and download it. All right, and may I bring your attention to your audience that if your day-to-day job is not connected to web application firewalls, you may be still interested in that, because not only WAFs use regular expression for security protection, but this is also used from the very high-level cross-site scripting auditors, filters in Internet Explorer, for example, down to JavaScript functions on the front end, down to backend code. So, yeah, I just giving a quick demo about the tool with the example how you can use that to find security faults. Here I just git cloned the GitHub which I was presenting. All right, so this is a script written on PHP. Come on. All right, so it says that I should specify the file here, and I already have some examples of regular expressions here. All right, so let's take call rule set 2 -SQL and use it as an input. Right, it works, done, output file is saved here. So it basically takes a file as an input and it produces an output HTML file highlighting all the problems regular expression have. Right, can you see that? Yeah, so line 1, regular expression from call rule set. Regular expression should avoid using magic characters for the start and the end of the string, and this is highlighted here. Regular expression is possibly vulnerable to redos. You should verify that manually. Right, number set a group should be carefully used. Let me show you another one. This big regular expression is used for preventing from SQL injection attacks. As you can see here, from between the keywords from and where, the regular expression is attempts to find at least one between 1 and 100. I'm not sure if you can see that. Between 1 and 100 symbols, but in case you specify more than 100, you can basically bypass this not the whole, but this part of the regular expression. So that's it. I know you all came here to watch how big names in security are bypassed. So this is the rule from Mod Security call rule set, the latest version 3 release candidate. And if someone told me before my research that I will bypass Mod Security in a so easy way, I wouldn't believe him, because there is Mod Security org which has the script in verifying and testing the user input. So you may specify HTTP colon double slashes and AP address, and it will find the remote file inclusion tag here. But when you uppercase any of the symbols, say TT, it will not find an tag. So this is as simply as using is understanding that regular expression should have case modifier I in it. Well, Komodo WAF has some of rules which are compatible with mod security WAF, and they're developing their own rule set. And they simply take the core rule set of mod security or OWASP as the basis and modify that slightly. As you can see there, I'm not sure if you can see that. I'm sure they have a laser. Right. The logic of the regular expression here was changed because of the additional backslash here. And this regular expression is not now searching for the on header events, such as on error, on load, on mouse over, whatever, but it is now searching for the opening bracket A to Z, opening bracket A to Z, because the logic of the regular expression has changed. So this blocks the simple string, which doesn't mean anything, but it doesn't block the attack now. All right, quick defense WAF also thinks that attackers are lazy enough not to include too much spaces between the keywords union and select in this example. I mean, this issue could not be found using black box analysis, because I cannot imagine an attacker inputting like 99 spaces, 100 spaces, 101, pass. Yeah, so you can only find that during static analysis of the rules. And this is the example which I found in one of the bug bounties while I was inspecting the HTML code of the web page. I found the following JavaScript function, which part of those is vulnerable to regular expression denial of service. And since you can supply the email into this function, so it will evaluate for a longer time, you can simply attack any user. And when I tried the attack to face myself, my browser simply crashed and the tabs were gone because of the denial of service. And I thought, what if I would supply the same email into the backend, because developers do not usually trust the user input data from the JavaScript, and they usually try to verify everything coming to the backend using maybe same regular expression. So I thought, what if backend is also vulnerable for the regular expression denial of service? And I posted the same email, and yeah, it was. So I have occasionally denial of service the website through the regular expression here. It's also nice. Right, now I'm going to present you the regular expression which is used in all versions, I think, of Internet Explorer family. I mean, beginning from Internet Explorer 8, I think, until the age 12 or 13. Here, regular expression looks pretty nice, but I think you can spot the flaw here. Can you? All right, I'll be talking about that. So this attempts to search for the word in, followed by any symbol one or more time, because the plus is one or more, followed by the opening bracket, anything after the closing bracket. So if you will supply the string which matches this pattern, opening and closing brackets will be substituted with a hashtag sign, and the attack will not happen, and the filter will block that. But as far as we know, repetition in symbols, using plus in repetitions instead of asterisk, which means 0 or more, is not a good idea. So if you will supply 0 spaces or 0 characters between the word in and the opening bracket, it will result in bypass, as simple as that. So this works in age 12 or 13, I think. So this is the screen of the latest filter of the browser. Yeah, and this is actually my favorite flaw, which I found in mod security first. Then I found the same error in PHP IDS. I found the same error in the previous version of mod security version 2. Can you spot the mistake here? I think you can. yeah, there is a white space after the word not. And this regular expression is simply searching for between white space one more time, character, and white space, one more character, not white space, the second white space, and the character. So it simply attempts to find two white spaces between the not and the character, and it can be simply bypassed with using one white space. Well, when I went in to dig the root cause, I found the page on the GitHub referencing to 2008, actually 8 years ago. And I found the initial comment which changed the logic of the regular expression, and there was a white space included here. And I have evidence that since the rule writers those times were not weren't experts in all the kinds of attacks, they copy-pasted or inherited the rules from each other and input into their WAF. As soon as I found the same issue, I mean the white space, into PHP IDS, more secure version 2, more secure version 3, and some of the other WAFs I can name, can you imagine how many WAFs else developing after 2010 have copy-pasted the rules from all those big names? I mean, more secure and PHP IDS. So, yeah, that's pretty interesting thing, I think. Right, what's next? You can tell me, Vladimir, all right, you can try to find flaws in regular expressions. I mean, they can be a lot of, but what can you do with them? Well, I can answer that. You can identify WAF vendor and version using signature vulnerabilities. So this is simply applying not to white spaces character to see whether the page is blocked, and not white space, not one space character to see where it is not blocked. So you can identify the family. After that, you can reveal bypasses depending on the situation. So you have SQL injection where this particular payload, and you have the bypass for the particular payload, but this is not very likely, right? And the most interesting thing is you can try to craft the string which bypasses all rules of all regular expressions of the current rule set. So I'm just going to show you how to bypass the most security latest version 3. So given the simple injection into the string parameter ID here, you can craft the following text or the string, and it bypasses all rules based on regular expressions of mod security version 3, I mean the latest version. But the mod security uses lib injection for detection of SQL injection attacks. And that library detects this attack here. Well, that is good enough, but not enough. So we're going to dig deeper and find the universal bypass, right? All right, I would just go through that pretty fast. The method 2 of finding logical bypasses during manual review analysis has been here for ages. So I was just skipping that pretty fast just to mentioning the contribution. Well, the blacklist is always a fail because as far as researchers go, they can identify new vulnerabilities WAF creators didn't think of. So this is the screenshot from the Elasticsearch, I think one of the latest versions. And it is vulnerable to HTTP response splitting due to usage of the native web server. So the vulnerability here, the vulnerability exists because after the new line symbol, you have to input either the white space or the tabulation, and so the header is a bit modified. But this is not an issue for Internet Explorer, where you can adjust that HTTP response splitting and execute any code after that. And if mod security will be protecting the Elasticsearch front end, or the API, it will not detect the attack here because it is searching for new line symbol followed by any of the headers, and it is not searching for the white space or a tabulation. You can find lots of bypasses while bypassing the blacklist, so this is not anything new. And also wanted to emphasize that researchers succeed, and Mazin Ahmed, I'm not sure if he's here and listening to me. Well, he had the white paper saying that there is some UTF-8 bypassing Internet Explorer of the older versions, 7 or 8 or 9, I think. And the mod security wrote the following rule, and you can bypass that also while doing a bit more research after the research. Yeah, and you all know like this fail, all right? Yeah, method 3, unexpected by primary logic bypass. By that method, I mean finding such logic finding such types of injections which did not exist in the brain of the rule writer or the maker of detection logic. The way how you're going to do that is, of course, fuzzing. I'm not inventing here anything new, but you can write XSS fuzzer. You can make a lot of virtual machines on your VMware or whatever it is. You can use all the browser emulating websites where you can test your payload in the web browser. You can try to insert various symbols into different types of the payload. You can run various tests. You can collect all the data from the research. You can collect the user agents to parse it all and to find which symbols are allowed in which user input in which browser. I'm not discovering America here also, but I can show that it can be pretty fast, and you can discover new attacks that could not detected by any web application firewall. For example, the Microsoft Internet Explorer version 9 allows null byte symbol in any types of the payload. I mean, you can write it any times you want everywhere. I mean, in the middle of the starting of the tag name, for example, and that could go undetected in the mod security version 2, which is by default can be downloaded from the mod security repository. All right, here, but libinjection. Back to that. Libinjection is the library which was first presented, I'm not sure about first, but which was presented here on Black Hat 4 years ago, I believe, by Nick. And the approach behind that is that it converts any input string into the sequence of tokens of length 5. So it does convert all the string parameters into the string token, keywords like union, or select into the key tokens of U and S. And after that, when the string is converted, the library is able to identify whether it is the malicious SQL payload or not. How is it doing that? I mean, how do you blacklist all those tokens? Well, Nick has collected all various types of SQL injection attempts from vulnerability scanners, published reports, forums, some close cheat sheets, and so on. When I accessed the GitHub of libinjection last time, I mean, about a week ago, there were almost 9,000 blacklisted tokens which are deemed as SQL injection if you input the string into libinjection. How you are going to discover all of those unusual syntax which gonna work on the SQL backend and which will not be detected by the library? Well, it's pretty simple. You can fuzz it. It just receives this SQL query as input. It's going to fuzz it using various libraries, MySQL.h, a native library of MySQL. You can use the SQL API.h from, I believe this is a commercial library, but it can be used for some time. And you should record all the queries except syntax errors to identify whether the payload you're fuzzing is working or not. And I can say that's pretty fast. On my virtual machine, which was running just one core of processor of the CPU and about 1 gigabyte of the memory, the speed was about 9,000 queries per second. But MySQL can go up faster, up to 1 million or more. So this is the example of the fuzzing binary, which is, so the first screenshot measures the time of the executive of this binary, and I'm inputted in, and I'm using select xxx from something as input, and it is fuzzing 3 characters between the keyword select and 1. So it has worked about 40 seconds or 38. It could be much faster anyway. And here, in these 38 seconds, I have found 13 total unique vectors which are bypasses for libinjection. You can see some of the some of the examples of these vectors here, and the lib injection token, which is in the left column. So all these examples are bypasses for lib injection. Let's construct, so after we have all the theory, after we have all the examples, let's construct such tokens that can bypass it. As you can see, let's choose the token breaker, this one, as a token breaker for the tokenizer. So when the select one from test is blocked, you can use this token breaker to go attack undetected. So that means that using everything after the token breaker can be written without any detection. For example, you can use out-of-band load file function or anything you like. And you also can use your simple union-based SQL injection if you have the token breaker here. And set union, select token breaker. After that, password, credit card number, CVV from users, database, union, select everything after that. That could be they're going to be undetected here. Yeah, and the biggest contribution, I believe, is as a result of this work, is the table of the results. Here I have used this. Here I have several runs of the C++ fuzzer on several backends, say MySQL, MySQL on this slide, and I have passed some injection points. So -1 union, you have allowed symbols shown in the table. Select one, you have number of allowed symbols which you can use. And when another time when you face the web application firewall and you believe that you can bypass it, but you don't want to write your own files, or you don't want to waste time on finding that, or maybe if you're the rule writer, you want to understand which symbols are allowed in which injection point, you can use this table to maintain your rules. All right, so I'm pretty close to the end. I'm just wanting to once again repeat the contribution here. The first method showed that regular expression security cheat sheet is possible to write, and now it is live. You can I have also coded the static analysis tool, which you can run through your regular expressions, blacklist improvement, and SQL fuzzer classified tables. Please access my GitHub to download that all. And as a part of future work, I encourage everyone interested in that kind of research and that parts of it to contact me to evaluate new techniques and improve all the tools we have. Well, regular expression security cheat sheet needs to be constantly updated because well, I didn't do this on my own. I involved several colleagues of mine to do that, but I mean, 2 or 3 people cannot cover all possible evasion techniques, all possible flaws of regular expression. So I really appreciate if you will contact me, and we're gonna make a new pull request and constantly update that. Well, the regular expression dynamic analysis tool is also a really important thing because using static analysis tool, simply watching at the source code of your as your source code is not enough to find all possible mistakes, and you can not understand what the part of syntax you're on. So I'm going to do that also in the future time. The third thing is clever fuzzing. That said, what I mean by clever is not using only one input into one injection, but also using several inputs to find constructions which are not very obvious to detect and to find out. This can help to discover unusual syntax of databases to pawn the web application firewalls. I mean, constructions such as select, I don't know, one, comma, function, opening bracket, something inside it, comma, closing brackets, something like that. Yeah, and scale it, because MySQL allows up to 1 million queries. I mean, things can go really fast. and you can find lots of interesting things here. All right, so thank you all of those people mentioned on the slide. Thank you to the audience for listening, for the presentation. Once again, thank you.